actually presented in my third visit to Ireland. I presented this talk as I was talking to Raphael earlier at the CASI meeting in 2019. So apologies if anyone was there, but now the good news is I only presented the work as work in progress. Now we've actually completed the work and we're just about to submit a paper on it. So the work's been a few years working through, and it's been joint with Blanca Sarzo and Victor Elvira. Victor is a reader in the School of Maths at Edinburgh with me, and Blanca was a PhD student at the University of Valencia, and she started this work when she came to visit me on a research visit to Edinburgh. And then she went back, completed her PhD, and now she's a Margarita Salas Fellow at the University of Valencia, which involves coming back to Edinburgh and working. So now we've managed to finish off this project that we started during her PhD. So Blanca has done a lot of the hard work within this talk, and in particular a lot of the coding. So what am I going to be talking about? Well, for any of you that know me, it probably won't come as a surprise that I'm going to be talking about capture-recapture data. Those of you who are not familiar with capture-recapture data, I'll give you a brief introduction into the type of data and the models that we often fit to the data. And then what's new recently, perhaps, when we want to be looking at analysing such data, is that some of these studies are over many, many years, and the amount of data that we're now collecting has accumulated. So now we have what for capture-recapture can be sort of large data, and by large I mean the number of individual animals that we see within the data set. And for the data set we're going to be looking at with some guillemots, I think they're up to about 50,000 birds now that they can have uniquely identified. And we'll see how they do that in a minute. So this is what I mean by large. It's large relative sort of to the traditional types of data set that we may have. And that creates some new challenges for us. And this is how the work developed, that we wanted to fit some models, some relatively standard models in some sense to the data, but because of the number of individuals in the data set, we started having computational problems. And this led to this work then of, okay, how can we develop efficient algorithms in order to fit what are relatively standard, hence not very complex models to these data set when we then start having large numbers of individuals, which creates problems with some of the techniques we have used in the past. So I'll present the method for what we're going to do, these new algorithms, and then I'll present results from two cases. One is a very simple simulation study, sort of proof of concept, and then we will go back to the data set that's motivated all these problems and see how we fit it there to a much more complicated model. So what is capture-recapture data? Well, it's quite a long history to collecting capture-recapture data. We're focusing on capture-recapture of animal populations. So we're interested in some, in our case, particular species of animal, and we're going to be looking at a colony because we're going to be looking at some birds, and we want to understand better what's driving those population over time, and in particular we're going to be interested in, for example, survival probabilities. And this is probably very important for conservation and management and so on more generally. So we want to learn about the population we're interested in, and in particular we're going to be thinking about survival rates, so we have to do this temporally over time. So we're going to go to our study site over a period of time. For simplicity, just about talking about this, we're going to assume that we go out once a year to the given area. In our case, I say that's a colony. And when we're there, all the animals that first time we go out to the population, all the animals that we see, we capture, uniquely mark, and then let them go. The second time we go out to the population, to the colony, we do exactly the same thing. All the animals that we see, we now capture them. I'll come back a little more specifically what I mean by that in a minute. But what we see, and then any animals that we haven't seen before, we will uniquely mark and let go. And any animals that we have seen before, because they're uniquely marked, we know that we've seen that animal before, so we record that we've seen it, and off it goes. And we keep doing this time after time after time over a series of capture occasions. Now, traditionally, we would uniquely mark individuals using either a tag. So on sheep, they put a tag in its ear. On birds, which is in our case, they put rings on their legs. There can be different types of rings. Metal rings with a number, for example, to identify them. Sometimes they're plastic rings and so on. More recently, something I'm not going to be talking about today in terms of the populations we're looking at, but you can also not actually have to physically capture an animal and apply some artificial marking, but they may actually have those individual markings easily enough by just how they look. So for great crested newts, they've got pelage on their underbelly that's unique. We can use those for leopards, tigers, and so on. The paternations on their skin, we can use those to identify the animals. And for some animals, that's very, very advantageous, like tigers and for example, then snow leopards, because actually they're very elusive to find as well. All right, so that's sort of the process for collecting the data. And then I don't do any of that. I sit in a nice warm office in front of my computer and talk to ecologists that go and do this. And what they then do is they collect the information and give me this information in a nice simplified form. So what I basically have is a big matrix of zeros and ones. And the rows of the matrix corresponds to each individual unique animal that they have seen across all the different capture occasions, and the columns of the matrix correspond to the capture occasion, and then the elements of the matrix gives a 0 if that individual in the given capture occasion is not observed, and it gives a 1 if the animal is observed. So for example, row 2, we've got an animal that was only seen, or individual number 2 was only seen at capture occasion 2 and then wasn't seen through any of the other occasions. Alternatively, individual 3 was seen at time 2 and 4 and not seen at other occasions. So each row is now called a capture history for each of the unique individuals that were observed within the study. And so this data has been collected for decades. And what we're going to be interested in, there's many different types, but based on the assumptions that you have, for example, whether the population is closed, so there's no birth, death or migration, so you've got a constant population that you're able to observe, or whether it's open, where you may have entrance into the population either through immigration or birth, and exits on the population for death or emigration. Then you can develop different models to analyse the data. We're going to assume that we have an open population, which means that we have births and deaths effectively. And then the models of that model, the parameters, sorry, of that model, we have two forms. We have a survival probability, which is typically what we're interested in. And we have a capture probability, which is really a nuisance parameter, but it's an observation process of what we have because we don't observe all animals at every single time. It's typically much less than 1. So that's, and then this is then work on these types of these assumptions were developed in the 1960s. The famous one is the Cormack-Jolly-Seber model. So that's the one we will be looking at in a minute. So let's look at the data that we're actually going to be looking at. So I said this is going to look at Guillemots, which is a colony of birds close to Sweden on a big island. And it's the largest colony of guillemots in the Baltic Sea. The study's been running for quite a while, I think 1990s at least, up until it's still running. But we're just going to look at a subset of the data from 2006 to 2016, so 11 capture occasions, 1 annual time each year. They go out, and within that time we see 30,000 individuals. Now all birds are ringed as chicks, so all the ones all these individuals we know are chicks when they are ringed, And then we don't actually physically capture them following that initial ringing, but it's done via long-range telescopes. When we re-sight individuals, they look at tags that they place on their legs, and we can uniquely ID them from that. And then that's our data. So it's a re-sighting rather than a physical recapture. So this was what Blanca was working on when she came to visit in Edinburgh a few years ago, and we started to fit some models, in particular this Cormack-Jolly-Seber model to estimate survival. But there was some, we weren't very happy with some of the fit of the model to the data, which has then motivated the work I'm going to be talking about now. But when we were fitting the standard Cormack-Jolly-Seber model, it's very straightforward. We've got an explicit expression for the likelihood. We fit the model to the data. We can get estimates of survival and capture probabilities. So what is this Cormack-Jolly-Seber model, which I'll refer to from now on as CJS? You don't need to worry too much about it. I'll show you the main things we want to take away from it. But the main thing is we have two sets of parameters: survival and recapture probabilities. We'll often have some dependent structure for these parameters, so time dependent, age dependence. They're the two primary ones we're going to be interested in. I'm not going to go into how we select the time and or age dependence, but we're just going to assume we have a model that we want to fit for these. And then we have to write down a likelihood function. So what's the likelihood function of the data? And that's relatively straightforward. All we need to do is work out what is the probability for each individual, what's the probability of their given capture history. We also, within that probability of their capture history, then we condition, the thing about the CJS model is we condition on the first time that we see an animal. That means we can't actually estimate arrivals into the population, but we can estimate the exits or the survival probabilities. So if we can calculate the probability of each possible capture history, then the likelihood is very straightforward. We just product over all individuals because we assume they're conditionally independent given the parameters. And we just product over each individual of the corresponding probability of their capture history. So that's very straightforward form. Their capture probability, so the probability of their capture history, given the first time they're observed, is also relatively straightforward to write down. So if we look here at this function here, this is saying this is what is the probability of being observed at times, well, 3 and 5, given that you were observed at time 3. Well, we have two parameters. Phi is the survival probability, P is the capture probability. We condition on the first time we're seen at time 3, so we just look at what happens thereafter. Well, we know we must survive the first year from time 3 to time 4 because we've seen a line at time 5, and once you're dead, you stay dead. So we'd have a phi 3, the probability we survive from time 3 to time 4. We're not seen at time 4, so we have probability we're not observed. We survive until time 5. We are then observed again at time 5, capture probability at time 5, and then we have the probability we're not observed after time 5, which we don't know whether they're alive or dead at time 6, so either we have to take into account both possibilities, either they survive and they're not seen, or they die, and if they die we cannot see them for this particular model. We can only observe live animals. So main thing is we can write down this likelihood. So that's straightforward. It's closed form. Off we go. And this is the basic model. So this one came about in the 1960s from Richard Cormack, George Jolly and George Seber. So that's only sort of the basic model. And often then we're interested in developing these models further because they might be a bit too simplistic, or we might be interested in some other parameters that not a thing like migration parameters or movement between different colonies and so on. So that is the basic model, and then we can add to that. And there's many different ways that this model has been extended. We can extend to allow for covariate information in terms of discrete covariate information. So whether you're male, female, you can add in then whether they're time varying discrete states or when they're moving between different colonies or different life states. And so on. We can get this more and more increasingly sort of differences dependent on what's being asked and the available data. The one I'm actually going to, I'm not going to go through all the different possibilities. The one I'm going to be focusing on is often we want to allow for individual heterogeneity. Birds might be of different quality, but we don't actually observe anything about their quality. So we have an unobserved continuous sort of individuals covariate. And to model that, we do some random effects model. So what we assume is our survival probability is simply some function with an intercept. Here we have a time-dependent intercept. So we have a different survival probability over time, so they may have different environmental conditions and so on. But we then have an additional random effect for the individual, and we just assume that that is normally distributed. So it's a random effect model. And then that's great. So now we're allowing individual heterogeneity, so there's this unobserved quality or whatever we might want to think about what this may be. And we just want to do exactly the same thing we've done before. We go, okay, we now got this slightly extended model, very, very simple extension of the model. And we just want to fit that to the data. That should relatively be straightforward. The problem comes when we have random effects. Again, this is more general, not just in terms of these types of models. What we have to do in our likelihood function is integrate out over those random effect terms. And that's where the problem comes in. When we want to actually calculate the likelihood and integrate out those random effect terms, the likelihood is no longer available in closed form. So remember previously, our likelihood was we product over each individual and then we calculate their probability of their individual capture history. So now, this is our likelihood now, given the parameters alpha, if we knew epsilon, then we can write this down. So we write this down, so phi is just a function of alpha and epsilon. So it's again exactly the same expression we had for the CJS. We then have to account for the random effect distribution, and we have to integrate out over these epsilons, integrate out those random effects to then get back to our what I often call the observed data likelihood function. However, the form of this expression, is one reason I wrote down the likelihood earlier, is no longer closed form. We can't do this integration. So now we've got an analytically intractable likelihood. So we can't do this directly. We can't just maximize this likelihood directly. So again, if anyone knows me, it won't surprise you. The first thing I would automatically do if I was doing that would be Bayesian. I'd be Bayesian, and then I can do data augmentation and solve all my problems. So let's just do that. So now we want to do a Bayesian approach, and the trick with Bayesian data augmentation is that we treat those epsilon values as additional parameters or auxiliary variables that we want to estimate, and then we form the joint distribution over the parameters and now these additional auxiliary variables. And that we can easily do. So this is what we have here. Now I've expanded our posterior space. It's not letting me highlight this because it's an equation. So we've got our posterior distribution now, not only just P alpha and sigma squared, which are the parameters in the model. We've extended that and have it jointly over epsilon. Turn the Bayesian handle. We can write this down as proportional to the likelihood. I seem to have forgotten my priors. So there should be some priors there as well, sorry, at the end. Our joint likelihood now over the observed data and random effect terms, plus all the priors, which are missing. And all these now, this is all now available in closed form. The integral has gone away because we're treating the epsilon as parameters. And we can just do a standard MCMC algorithm and using your favorite algorithm or writing one, your favorite black box software or writing one yourself. And we can just sample from now this joint posterior distribution. But of course, this isn't the posterior distribution we wanted. We only want the posterior distribution over the model parameters, P alpha and sigma squared. So what we do is we can just marginalize our output really easily by looking at our sampled values of the P's, alpha, sigma squared and epsilons, ignoring the epsilons. And that does our integration, our marginalization to get our sample from the posterior distribution that we're interested in. So really straightforward. Bayesian data augmentation turning handle exercise. Except, think back to this now, I've got, for the data set we're looking at for those 11 years, 30,000, just shy, individuals. So if I'm now wanting to do a Bayesian data augmentation approach, I initially had, well, for the Guillemot data I have later, I've got 18 parameters because of the dependence for the survival and capture probabilities. So I've got 18 parameters, but my dimension of my posterior distribution is now close to 30,000. I've had to add in 30,000 different parameters corresponding to the epsilon i's to do my standard Bayesian MCMC handle turning exercise. And that makes it go very slow. So it might be possible. We did manage to fit some simple models in JAGS we were using at that point, but it was taken over a week, and that was a really simple model, not the model we wanted to fit. And it's not, unfortunately, just these extra 30,000 parameters we're having to update at each iteration. It's more, there's some more nuance than that as well, because the correlation that we have between particularly the epsilon and the sigma squareds is really, really large. So we get really poor mixing as well. So we've got a slow chain because the number of parameters we update, and it's a poorly mixing chain, and everything sort of grinds to a halt, and we couldn't fit the models we wanted to do. So that was all the backdrop to actually, okay, can we fit these models in a more efficient way? So the idea is as follows. We can't sample from the posterior distribution we're interested in because it's just too high dimensional, it's too slow and so on. But what we want to do is simulate from some other similar distribution for which it's really quick to simulate from, which I've donated by G. And then given that sample, given that sample from that distribution G, can we then correct that sample such that those sample values or corrected sample values come from the actual posterior distribution that we're interested in? And that's the whole idea. It's a relatively simple idea, I think. Rather than sampling from the posterior distribution we want, we'll sample from something slightly different and correct. And the way we correct for those sampled values from not quite the right distribution is via importance sampling. So we simulate our theta values from G, simple distribution, and then to do importance sampling, we obtain our weight, which is a function of the posterior distribution we're interested in, and the actual distribution, this cheaper distribution we've simulated from. So it's of a specific form. And then we can use those in order to do an importance sampling estimate of the posterior distribution, either just using a weighted. If you want the posterior mean of a parameter, you do a weighted mean where the weights are given by these WIs, or we would do a sampling importance resampling algorithm. We've got our sample values theta, each has a weight, and we just resample with replacement proportional to the weights for each of the sample values, and then that gives us our sample from the posterior distribution we're interested in. Now, lots of questions probably spring to mind is, okay, we can do this, but the most obvious question perhaps that does spring to mind is, okay, what is G? What cheaper distribution do we use? And the critical part of this with importance sampling is that we need G to be close to the posterior distribution. Otherwise you get basic particle depletion where you can have all your weight, all your mass on one weight and nothing for all the others, which is obviously not a good thing. So we need G to be as close to possible to the posterior that we're interested in as possible. So in order to define our G, I'm going to sort of take a step back and go look at the, think about the posterior distribution that we're interested in. So we have the posterior distribution, and I'm just going to use theta now for all my parameters for simplicity. Posterior distribution of the parameters given all the data that we have. That's simply proportional to the likelihood times the prior. Now remember, our likelihood is such that we product over each individual and calculate their corresponding probability of their capture history. So in other words, the individuals are independent, so we can just product over their individual contributions for each individual in the population. So we can split our likelihood up if we want, rather than writing it as over each individual in the population. We could sort of think of two groups. So we can partition the individuals into two groups. So each individual belongs to one and only group, group 1 and group 2. And then we can write down what's the likelihood of that, again, we can write down as the likelihood of group 1 times by the likelihood of group 2 because they're conditionally independent. So this is what, again, this isn't going to, oh, it is going to highlight. This is what I have here. So we have likelihood of group 1, likelihood of the individuals in group 2 times the prior. But if we just look at this bit here, oh, this should say now proportional. We have the likelihood of the data x2 given theta times the prior for theta. This is simply the posterior distribution of the parameters given the data x2. So we can rewrite this as simply as a prior. So all we have here now is our posterior distribution is the likelihood of the data x1 given the theta times by the corresponding prior, where that prior is the posterior distribution of the parameters given the other part of the data x2. So that motivates what we're going to do. We're going to split up our data into two parts, and we're going to treat our G to be the posterior distribution of just a small part of the data set. So we have our two data sets. I'm going to assume x1 is most of the data and x2 is a sort of just a smaller subset, but they're a partition of the whole data set x. And we're going to treat our cheaper, simpler distribution that we can sample from to be the posterior distribution of the parameters just given the smaller data set. And I'm going to call that the sub-posterior. Now, because x2 is small, we can go back to our Bayesian data augmentation approach again. We can just use our standard MCMC to get a set of sample values from that posterior distribution, or this sub-posterior distribution. Back in old world territory, when we have small data sets, everything works fine. It worked fine when we had a small data set, so we've created a smaller data set. And again, we can just use whatever favourite package we have. So that's how we're going to define our G to be this sub-posterior of the parameters given a small part of the data set. So we now can sample those. Now we have to calculate our weights. And if you go through the maths, you take the ratio of the true posterior divided by the cheaper proposal distribution or sampling distribution. If you just expand them out, we can write down that the weight is now simply equal to the likelihood of the larger data set given the parameters. Great. Apart from we've gone full circle now. We can't evaluate this weight. The whole reason where we started doing this was because we had an analytically intractable likelihood. Now I'm saying we have to evaluate a likelihood, but again, it's analytically intractable. So does that mean, okay, I basically just reinvented the same problem? Thankfully, no, because we can evaluate this numerically. And there's a very nice result shown by a paper in Tran et al. 2016 that if you replace the weight by an unbiased estimate of the weight, we still have the correct distribution that we're interested in. And it's basically the same argument as particle MCMC for those of you who are familiar with that. I'm not going to go into the details. So all we need to do, rather than being able to evaluate the likelihood explicitly, which we can't, we can actually, as long as we've got an unbiased estimate, then we're fine. So all we need to be able to do is to obtain an estimate of the likelihood. So I'll explain how we do that in a minute, but hopefully I thought I did it before. No, okay. So I'll explain how we do that unbiased estimate in a minute. So, okay, so just a summary, what we have to do, first of all, is partition the data, run an MCMC on the smaller data set, and then feed that into the importance sampling algorithm to calculate the weights. We do numerical integration to obtain an unbiased estimate of the likelihood. So lots of questions probably then spring to mind. How do we partition the data? I've just said we do this, but how do we do that? And then how do we obtain an estimate of the weights? So there's other things that are going on as well, but they're the two things I'm really going to focus on. So how do we split up our data into the main of the data x1 and then the smaller x2 for which we're going to do our MCMC on? Remember that we want the posterior distribution of the parameters given x2 to be very, very similar to the full posterior distribution of parameters given all the data. So really what we want is the x2 to look very much like the full data set. So we're going to take a stochastic approach for doing this, and hopefully that'll become clear why later we're going to do a stochastic approach. But there's many different ways we could then do sample the data to get our x2. Random sampling, just randomly sample them, typically not a good idea, it's too much variability. Stratified random sampling, where we're going to try and reduce the variability that we get by making it look a little bit more hopefully like the dataset. We're going to consider stratified, so we're going to specify strata for the different individuals, put them in, and then sample proportionately to those strata. And that typically might do the year of release. And we do what I'm calling a double stratified approach, where actually we define each strata, we group individuals together for which they are released at the same time and seen for the final time at the same time. So all individuals that have that pattern are put into the same strata, and then we simulate, subsample the data proportional to those strata. So just to give you an idea, so these are the three schemes I was talking about. Random sampling, we just randomly sample so many individuals. Scheme 2, we condition on when they're released. So all the ones that released at time 1, irrespective of what happens after, all in one group. And this is the more important one, which works best, as we'll see in a minute, where we condition on first time of release and when they're last observed. Because remember, survival is what we're interested in. So whenever they're last seen, that's when we know they're all alive for the last time at least. So that gives us something about information about survival. So to give you some idea of the variability of the sub-posterior versus a full posterior, so this is just some simulations we were doing. The grey is the full posterior, using all the data, and then we did different sampling, subsampling techniques, calculated the posteriors and see how much variability are they. The first row is scheme 1, where we just do random sampling. You can see the sub-posteriors, which are these coloured ones, are quite variable, and they vary quite a bit from the full posterior. If we do this double stratified sampling, then there's much less variability and there's a lot more overlap for all the different cases with the full posterior. So that was a good thing to do. That is important to get in the subsampling right. The second part is, okay, well, we split the data up into 2. What proportion do we put in each of the different data sets? We need the amount of data that we need to put into the smaller data set, x2, needs to be small so we can run our MCMC, but it needs to be large enough such that we get posterior distributions that look similar to the full posterior, ideally. So we did this via some pilot studies, and we just tried out different percentages between basically 5 and 30%. And we sort of settled on 20% seemed to work quite well in the different simulations that we considered. It was large enough that our sub-posteriors were fairly consistent and looked fairly similar to the full posterior, but still wasn't too long for running MCMC. So when you started increasing it further, you weren't getting that. It was like diminishing returns of how close they were to the full posterior. So we're just going to stick with 20% now. The second step in this algorithm is the important sampling steps of calculating the weights. And I've said the problem is the weights don't have a closed form. We have to estimate the weights, and ideally we want it to be an unbiased estimate so that we get the theoretical guarantees of the correct posterior distribution. So the way we've gone about obtaining the weights is to use a stratified Monte Carlo algorithm. And just this other thing I should say is that the weights are a product of one-dimensional integrals. So all we have to worry about is a one-dimensional integral. It does make other methods also possible. So we're going to do a stratified algorithm. So we just based it down on quantiles. One thing I will say, we did cheat a little bit. We no longer have an unbiased estimator. We only had a consistent estimator, because the number of times you have to do this is the number of individuals that are still in your X1. That's the number of integrals that you have. But a lot of individuals have the same history. And in some cases, 2,000 or 3,000 individuals have the same history. So we only calculated the integral for unique histories, sort of, and then used that and then took it to the power. We actually didn't do it quite like that, because we said the power had to be at most 200, because that also helped the convergence of the Monte Carlo estimate a little bit. But anyway, that's more of a technical detail, I won't worry, but basically short answer, stratified Monte Carlo estimate. Right. So now I'm going to finish off with that's the whole idea. So now we're just going to say, how does this work in practice? And first of all, I'm going to do it for a really simple simulation study. And then we're going to go back to that Guillemot data set and say, OK, can we work it on the Guillemots? So we did the simplest thing we could think of, where we only have 3 parameters in our model. We have a constant phi over time, constant p over time, and then the random effect variance sigma squared. We have 11 capture occasions, which is the same length of time as the study for the Guillemots. And we simulate just over 10,000 capture histories. The number for this we used is because we can actually fit the full model here. So we could do a standard Bayesian data augmentation on this model because of the small number of parameters, and still, 10,000 histories. But still, we could still get this to run in reasonable time for the full data set. So we can do a comparison, how well do when we know the answer. Oh, and I said here's the parameters, we have 3. So I've said before, we have 20% of the data. We're always going to use 20% of the data. We use the double stratified sampling scheme, subsampling scheme, which seemed to work relatively well, where we look at the first time and last time an individual is observed, and that defines the strata. And why we wanted to use a stochastic algorithm for subsampling the data is because we can do this, but if it's stochastic, we can simulate loads and loads and loads of subsample data sets. So we can implement this loads and loads of different times. So we actually do this 100 times. And then for each of these 100 subsample data sets, we put this through Nimble, 3 independent MCMC chains, fairly conservative burn-in, fairly conservative length and number of iterations to look for get to convergence. So then we ended up with 45,000 sample parameter values. Now we should note that the calculation of the weights doing this stratified Monte Carlo, it can get a little bit more computationally intensive to do that. So we didn't actually use all 45,000 sample parameter values to calculate the weights of those values. We actually subsampled those. We thinned them to only get 1,000 sample parameter values because that was enough, as you'll see in a minute as well. So we have 1,000 sample values, and for those we calculate their weights, and then from that, for each of the subsample data sets, we calculate the corrected posterior distribution. And the one thing to really note is this is really power. It's actually, we could do a double parallelization. We only did one because we're doing these 100 different partitions. These are completely independent, so we can just do this across multiple cores, which we did. So you're getting some free, basically you're getting some free lunch here. So let's look at the results. So we have set 3 parameters, mu, p, and sigma. So they're the columns. The top row is the marginal posterior distribution of the parameters of the sub-posteriors. So the posterior distribution of the parameters given the smaller subsample data set across the 1,000 subsample data sets. The second row is then the corrected estimates of the full posterior using, in order to get those, we did sampling importance resampling. The y-axis is the same. It's a bit small to see, but the y-axis is the same in both of the plots, or matching up. So for mu, these are the same y-axis, and so on for the p's and sigma. So you can see there's a little bit of variability over the subsample data sets. They're moving around a little bit. They're sort of semi-consistent. Similar for the p's and similar for the sigma, the sub-posterior. So, I'm not surprised if you think back to those coloured plots we had earlier. You can see there's a little bit of variability. Now, when we do the correction step, we get an awful lot more. These look very, very similar now. Because each of the subsamples, I would argue, these look very, very similar. They all give you a very similar estimate of the full posterior distribution. So picking any one of these, so pick any one subsample, you're 77, this gives us an estimate of the posterior distribution of mu in our case, and similarly for p and sigma. So that seems to work fairly well. But the one thing is, we've done this 100 times. I said we could just take one of these and that gives us an estimate of the posterior, but just taking one of them throws away an awful lot of information. We could combine these across but each of the subsamples, because each of them are independent estimates of the posterior distribution. So we can literally just combine them. That's what we did. Actually, I'll go forward and show. So this is what happens when we combine them, and you can see, and then this is now compared to the true posterior. So the black line is the true posterior, true, allowing for Monte Carlo error, analysing the data using the full data set, and the dotted line is the estimate that we obtain from combining all those 100. Well, I'm just going to nip back. One thing I would say as well is that we do get some particle depletion, as you always do with importance sampling, but we had 1,000 sample values to start with, and the mean number of what I'm calling non-negligible weights was about 200. There's a bit of variability, though, as you can see, between 79 and 260 across them. The interesting thing is the time. So going back to this slide now. So when we did this on standard MCMC, I don't know how many iterations this was run. I forgot to document that. But it was slow to run because we had now these over 10,000 parameters to update compared to 3 actual parameters because of all the individual random effects. And it was really slow, mixing wise and time wise. It took about a day. For the importance sampling approach that we had, it took about 10 minutes to run all the MCMC chains, and it took about 4 minutes to do the importance sampling. So we're down to about 15 minutes. And of course that's per subsample, but this could be done in parallel. So we were doing it in batch across several cores to do that. So that seems to work. So proof of concept, it works. Let's try it now on a slightly more complicated example, going back to our Guillemot. So we have just shy of 30,000 individuals. Again, we split the data set up. We consider 20% to be the smaller subset, and we're going to run our MCMC on that. Our model now is much more complicated. We have age and time dependence. For the survival probabilities, we have an additive age, time dependent model. There's 4 ages. 1 up to 3 and basically 4 plus is adults. So we've got individual heterogeneity plus age effects plus time effects for survival. For the capture probabilities, we have again age dependence, 2, 3, 4, 5 plus. If you add up all the parameters that we had, there's 18. Trying to do this is really hard to do this if we just wanted to analyse it full and run it into Nimble or JAGS, whichever you wanted. We've moved to Nimble by this point. Couldn't do it for the full data set, but for this 20% of the data set, we were able to get reasonable convergence, or actually more than reasonable, within about 45 minutes, 35,000 iterations after a 5,000 burn-in. Now to do so that was to get the first step on MCMC samples. Now we need to get our importance weights. Now, previously we had 3 parameters, and our particle depletion, we were losing about 80%. We were retaining 20% of non-negligible weights. We're going from 3 to 18 parameters, so 6 times as many parameters. We're expecting greater amount of particle depletion. So we did a little extra step when we did our weight calculation to try to be able to evaluate more sampled values. So basically what we did is we did a 2-step weight calculation. Our first step was to use a small number of Monte Carlo particles to get sort of a coarse approximation for the weight, and then we retain the top so many of those to actually calculate those weights much more accurately. And that really did speed things up, that we were able to then consider a much larger number of sample values from step 1 in step 2. So we considered 5,000 sample values. So we do this 2-step approach to calculate the weights. We retained, so we had 5,000 samples to start with. We do our 2-step approach. We retain the top 500 particles in step 1, in the first step, to feed into then doing the fine calculation of the weight. And that, again, from lots of investigation, this seemed quite conservative. So we weren't losing particles because of poor estimation. And yeah, we were doing this in about half an hour for these 5,000 sample values. And then what results do we get? So it's a bit hard. There's too many parameters and things going on. So what I've done is just extract some of the parameters for some of the 100 subsampled that we used. Again, it was another 100. So I'm just considering 10 subsample data sets and looking at the time-dependent survival parameters, which were the betas. The left-hand plot is our sub-posteriors again, so just each one of these lines corresponds to one subsample, and we've got 10 parameters. You can see that they're relatively consistent. There's a bit of variability. When we then do our corrected estimates of the full posterior, similar to before, we get the shrinking of the variability. But unlike the previous one, there's now a little bit more variability across these, which isn't that surprising, I don't think, given the added complexity of the model with the number of parameters. The thing is, I can't compare this to the full answer by running MCMC on the full data set, because we never got it to run in a sufficient time. So after a week, it was still running, and this is what prompted all this work. But we were able to get for each subsample, hour and a quarter. We were able to get an estimate. But again, the thing about this is we now had greater particle depletion, which was probably leading to some of this variability across the subsamples. We can combine them, which was really nice in order to do this. So to give you an idea of the particle depletion, again, I'm talking about weights with non-negligible, particles with non-negligible weights. The mean was now 35. Previously, it was about 200, and it's quite variable. Towards 67. So if you took any one of these subsamples, then you're going to have a relatively small effective sample size. Combining them across all the different independent subsamples then gives you much better and much more reliable estimates of the full posterior. And that's what we did here. So this is the same plot you had a minute ago, the corrected posteriors for each subsample, or for the 10 in blue, and then we did the combined one across now all of our subsamples. So we were able to get these in again reasonable timescale against infinity. So that's it basically. This started off being a relatively, well, just a bit of random effect model, individual heterogeneity model, into a full-blown project of how can we actually do this. It was just too computationally expensive. There are still lots more things that I think can be done to improve these things. Thinking about the subsampling schemes, what's important with understanding what's important with the subsampling schemes. I think we understood it for this case, but for other more general cases, we haven't done things most efficiently in several ways in terms of including the Monte Carlo estimates that we are using. We also, when we combine the different subsampled estimates of the posterior, we're treating them all with equal weight. The way we've done it, that's probably not the most sensible thing, because if you've got a bigger effective sample size for one subsample, you probably want to upscale that compared to one that's got a very low effective sample size, and so on. So there's other things we're trying to investigate to make this even better, and particularly to try and remove some of the particle depletion. But that's as far as we got. We actually managed to get this. We were able to fit these models, which we hadn't been able to do